We've seen why the value of our rate constant might change, but that presents us with a problem. Is remember, we need to determine the value of that rate constant experimentally. So every individual reaction would have to be tested at every possible temperature, finding rate constants for a varied amount of temperatures so that we could intentionally predict results in an industrial process. That is a lot of experimental work, and it's frankly exhausting. So there needs to be a way for us to calculate how that rate constant would change. And fortunately, there is. It's called the Arrhenius equation. However, this equation is very complex. We can see it right here. That is a giant pain in the butt. So instead of looking at it just like this, let's break it apart. Now, we're not going to need to do any calculations with this equation, but we are going to need to understand the relationships involved in it. So let's break this apart. Let's use separate colors. We'll use black for things like constants and just regular math expressions. And then we'll sort other things into different colors. And then we'll break it apart and look at it more specifically. So the Arrhenius equation, broken apart, made a little more colorful, a little less scary, looks like this. So we've got here is K. This is our rate constant. We have an A, and this A is known as a frequency factor. This is a multiplier that basically accounts for the different types of collisions and how they'll need to be aligned. This is unique to various reactions. So this is a multiplier. This E right here, this is Euler's number. This is a mathematical constant that's heavily involved in equations dealing with change. So this is just a number. That's not going to change. We just use it's like pi. So we don't really need to worry about that one. And then what do I have here? Well, R is my gas constant. And then E, this EA, this is going to be my activation energy. My temperature is T. So let's break this out one more time and really try to understand which things are constants that we're not really going to need to worry about. Let's go ahead and rewrite this one more time. Keeping in mind that we want to be looking out for K. K is our rate constant. That's the thing that we're trying to keep in mind. That's the thing that we're trying to track the changes of. So obviously we want to keep that in mind. A is going to be a constant depending on the reaction. This is the unique variable that we could find in tables online, or we could determine experimentally. E is Euler's number. We don't have a change for that. We just have a variable that represents it. And then R, the other thing we're going to have is R. That's our gas constant. That's a constant. We don't need to worry about that. So then the things that we do need to worry about are our temperature and our activation energy. We're going to have the negative for activation energy. And so when we use these colors to break this apart a little more, we're able to see that there's really only three different variables that we need to keep track of. So we're also able to linearize an equation like this by taking the natural log of both sides of the equation. If we do that, what we get is the natural log of K equals negative EA over R, and let's use another color for T, RT, plus the natural log, let's use one more color, of A. By modifying the mathematics of this equation, we could then graph this whole thing with our x-axis being temperature and our y-axis being the natural log of K. So that rate constant. We'd be able to then get a linear graph. So that looks like this. where our y-intercept would be the value of A. I'm sorry, the value of natural log of A. So we can determine that through a quick experiment and then using some minor graphing and algebra. And then our slope, the slope of this line right here, this slope would tell us activation energy over R. And so we can multiply this value by the gas constant and we'd get our activation energy. On top of that, we'd be able to see how our rate constant is changing at different temperatures. So we don't need to use this equation, but by looking at it this way, we're able to see how these different variables are related. We have this is the actual uniqueness factor in each individual reaction. But then we have an activation energy that we need to overcome, and a temperature that we're going to operate at. We're able to directly measure our temperature, and then using this information, we'll be able to predict the results of K. What we should take away from this is that by understanding the relationship algebraically of equations like this, we're able to use our knowledge of graphs and just these very basic concepts of a y-intercept, a slope, an x-axis, and a y-axis to get a lot of information about these very challenging concepts. We're able to tackle how something like the rate constant, which is dependent on energy, on collisions, on alignment of collisions, would be dependent on that temperature, that activation energy, and that frequency multiplier. We're able to see these relationships very well just by understanding how to graph these things in a certain way. So we should be able to walk away seeing how the rate constant is going to change based on the temperature and the activation energy.